Okay, so now let's look at the general equations of motion. So we have here a body, right? And so we have forces and we have moments acting on the body. There's a weight. In this case, the body is going to have a general plane motion. That means it's going to be translating and rotating at the same time. So the way we're going to describe that is we're going to have two options. We can study the motion about the center of mass, or we can study the motion about another point P. And doing this is going to be useful if we want to get rid of some forces when we are calculating the moments. So we'll see how that works. So if we want to study the body about the center of mass, then all we need to do is just write the equations of motion for the center of mass, x and y, and then the rotation for the center of mass, which is the moments about g is equal to ig alpha. And this is all we need to do, and this would be the easiest case that we need to deal with. Now, if we need to do the equations about a particular point P, right, that is not the center of mass, then the first two equations, they remain the same, right? So these are the translation equations, but then this changes. So the moments about P have to be equal to the kinetic moments. What are these kinetic moments? Remember, these are Ig alpha, and then this guy here, which is the mass times the acceleration uh, of the center of mass. And this, remember, these have to be multiplied by the distance from the center of mass to P, this distance here, right? So that's all. That's all we actually need to do. There's a type of problems where we have wheels and we have rolling, and so in that case, we may have something like this. We have a force P, and we have sort of a disk of a wheel, and it is rolling. So we can write the equations of motions, right? So, and we can write them about the center of mass. So we have the translation in x, the translation in y, and the rotation about the center of mass. So this equation just gives you that P minus F, which is the friction here, right? That's equal to mass times the acceleration of the center of mass. The vertical equation gives you that the weight minus the normal is equal to 0. And the rotation equation, that gives you that the moment about g, what is the moment about g? The only force is that is causing moment is this one here, right? So that's Fr. So that is equal to Ig alpha. So if you look at this equation, what do we have? We have four unknowns, right? We have this force, we have Ag, we have the normal, and we have alpha. Right, so those are four unknowns and we only have three equations. We need a new one. So here is when we do our assumptions, right? When we do our assumption. In the first case is not sleeping, right? So this thing is just rolling and this point is always at rest. So in that case, then the acceleration of the center of mass is alpha r. Remember, r is the radius, and then that's it. If we are using that case, remember the friction is not equal to this, so you cannot use that. The friction is always less or equal than the maximum static friction. The second case is when they're sleeping, and when they're sleeping, this point here is moving, right? And then there is a kinetic friction, and we use this equation for the kinetic friction. And this is no longer true. Those are the two cases. So problems, how do we deal with problems? So remember to draw your coordinate system and draw the free body diagram, and the kinetic diagram is useful. Then need to figure out the accelerations and what is happening to the acceleration of the center of mass and what is happening to the angular acceleration. And then if you're going to use a point other than the center of mass, then you need to write the kinetic equations. And remember, then you're going to have these two terms and you're going to have this term that appears in your equation. So then you write your equation of motions, then identify your known. If the problems are wheels or pulleys, then you need to make an assumption, slip, no slip condition, right? And then use the assumptions that you're going to be applying here. And then you may need to use the kinematics equations from chapter 16 and check the validity of this. So things to consider, remember to be consistent with the direction of the center of mass and the angular acceleration. If you're going to use this slipping condition, so the friction always opposes the motion. So let's look at a quick example. Here we have a truck that is accelerating 3 meters per second square. And then there is this tin here that is 500 kg, right? And it has a radius of half a meter. And there's no slip in here, so you don't need to make any assumption. They're already telling you this. So then what we need to find is the acceleration when the truck the acceleration of this tin when the truck has this acceleration. So let's look how to do that. So the first thing is, of course, free body diagrams and kinetic diagrams. So for the culvert, then we have the weight, we have the normal force, and we have the friction here. And there's no slipping, so I'm going to assume that the friction is pulling the culvert that way. For the kinetic diagram, we have what? The acceleration of the center of mass times the mass. And we have the rotation, which is going to be the moment of inertia times alpha. The moment of inertia is calculated here is mr squared. This is a simple cylinder, so that's 125 kilograms meter square. So that's the first step, kinetic diagram and free body diagram. So now let's write our equations. So we could do the equations about G or the equations about A. Let's write the equations about A, and if we do that, we don't have to deal with this force and this force that we don't know, right? So also, if we do the moments about A, there's no moment due to gravity, so this first side of the equation is 0 because there's no moments about A. So moments about A, which are 0, are equal to what? Well, these are the kinetic moments. The kinetic moments are Ig alpha, right? That's that guy there. And then you're going to have mass times acceleration of g times the radius. Mass times acceleration of g times the radius. So this is the first equation. So we have two unknowns. We need a second equation to solve this problem. So we go to chapter 16 and look at our kinetic equations. So the acceleration of point A is the acceleration of the truck, right? It's 3 meters per second squared, right? Because this point is moving at that speed, at that acceleration. So now we can write the acceleration of this point, which is equal to the acceleration of this point plus the rotation part. The rotation part is alpha plus alpha cross the the vector rg relative to a, which is this vector here, minus omega squared rg relative to a. So this vector here, that is rg relative to a. So then we can write that. So this is the acceleration, right? So let me just delete this just to keep this picture clear. So this is the acceleration, that is that vector here. So then you get the acceleration of the truck, 3 meters per second squared in the I direction, right? Then you get alpha k, right? So that's what we want to find. And then 0.5j is this vector here, which is this guy here is rj relative to a. right? Minus omega squared, and then again rj relative to a, same vector, right? And then I can simplify this a little bit and do the cross products here, and I get this. And then if I keep going, then this is what I'm going to get. I get that Rj is equal to 3 minus 0.5 alpha. So now I have a second equation, and I can mix that with the equation in the previous slide. So we can solve for those two, and let's just make sure that we remember what that equation is. We have the 0 is equal to 125 alpha minus 500 Ag times 0.5. So this is the second equation, right? So now I can go ahead and use those two equations to solve for alpha and Ag. So this is how these problems work, and then there are some examples in the coaching videos on the practice homework, and let me know if you have any questions.